Hello and good afternoon, and welcome to everyone here and those joining us on the Zoom webinar. Thank you for joining us this afternoon in the Masterclass in Physics. All right, and now before we begin, there are some housekeeping announcements. Please adhere to a safe distance of 1 meter apart and sit in the designated seats here in the LT. So please help me to check that there's no sticker behind you and you're not seated in the rows with a caution tape on them. Please keep your mask on throughout the masterclass as well. In the event of an emergency, please follow the direction of the usherers, which are myself and Anna here in blue, and evacuate in an orderly manner. We also kindly remind everyone to please put your phone to silent, and in the end of the lecture or end of the masterclass, please exit the lecture theatre using the door on the left. There will be a Q&A session at the end of the masterclass, but feel free to send in your questions during the QR code as you can see on the screen here. Visit the website polev.com Q&A LT26. I repeat Q&A LT26 to send in your questions. And for those joining us via the webinar, in the event that the Zoom session ends or disconnects, please rejoin us at the same link. Speaking today will be Professor Sow Chorng Haur from Department of Physics. He's also the Vice Dean of Outreach and Admissions at the College of Humanities and Sciences. During this masterclass, Prof Sow will share his experience in developing strategies to teach physics using science demonstrations that will provide exciting, visually appealing, and thought-provoking stimuli to promote a culture of inquiry and interactive teacher-student exchange in the classroom. So that this session will not ironically be all talk and no show. Let's hand the time over to Prof Sow to demonstrate what he really means. Let's give him a warm welcome.
Okay, thank you very much. So I can just go to my testing. Can you hear me? Can you hear me? Okay. I just go to my slide. Yeah. How do I share? Yeah, share
Screen and then
this side. Yeah. And then maximize. Is that okay? Good. Yeah. Let me just run. Okay. Yeah. So good afternoon, everybody. Welcome to the masterclass for physics sessions. And this is the last masterclass for LT26. So as introduced, my name is Sow Chorng Haur. I'm the Vice Dean in Faculty of Science in charge of Outreach and Admission. My day job is that I'm the professor in the Department of Physics. So the title of today's class is just to give you a sample of how classes are conducted in NUS should you go for any physics module. Some of you may be considering physics major. Some of you may be considering second major in physics, minor in physics, or just curious about physics. Okay, come, welcome. Yeah, go ahead. Yeah. So I have been giving this talk for years. I can't remember how many years already. So I always travel around in Singapore or even overseas and give this talk called The Physics Professor Suitcase of Traveling Science Wonders. So I would like to illustrate to the student, sometimes learning physics is kind of fun. Okay? There's a lot of exciting things you can do. And I want you to learn physics by developing models, concept, understanding as you see things happening in your eyes. Of course, we'll deal with equations and formula. That's essential, critical part for physics study. But I want you to be able to see beyond those formula and equations and understand what it means. And better still, you invent new things based on the concept. Okay, so yeah. A bit of introductions about myself. Okay, who is this guy standing in front of you? I was educated in NUS, so I completed my bachelor degree and master degree in NUS. Okay? And then I study really hard. Okay, my professor see me studying all the time. Hey, Chorng Haur, you like to study, right? I tell you what, I give you some money, you go and do PhD. Yeah. Oh, give me money, do PhD. Good. Give me money. Okay. Yeah, can sit anywhere according to instruction. Okay. Then, so I went to a place called University of Chicago and obtained my PhD. Yeah. After I got my PhD, I went to a place called Bell Lab to do my postdoc. That means after doctoral degree, you can do some more. Okay. to do more research and hone your skill as a researcher, becomes better and creating new knowledge. Then I come back, I become assistant professor. A few years later, associate professor. A few years later, become a professor. Okay, yeah. So I do a lot of research. I do a lot of teaching. Yeah. So my whole intention for the next 45 minutes plus is to show you learning physics is really fun. Okay, so what you need to do is to put on your thinking cap, and then when I ask you questions, participate in guessing the answer. Wrong, right, never mind. Okay, the act of participating in the answer and choose the answer helps you to really think through, engage in the mind map of forming understanding and concept to different things. Okay, so this is why I always tell students that the minds-on approach of learning physics is very important. Okay. So let me start off with this slide, which is a favorite slide of mine. 不闻不若闻之，闻之不若见之，见之不若知之，知之不若行之，学之以行而止矣。This is you throw rotten eggs at me. What are you talking about? I didn't say this. Somebody very smart many years ago said this. His name is Xunzi. He's about the third generations of Confucius in terms of the family trees of scholars. Okay, yeah. Let me translate into English. What it says here, rough translation, it says, tell me and I'll forget, show me I may remember, involve me and I'll understand. So I hope you understand that learning physics is not like you memorize things. We hardly ask you regurgitate Newton's law. Okay, we usually ask you to internalize it and apply it onto a certain problem. What I hear, I forget. What I see, I remember. What I do, I understand. So hopefully these ideas of having the participations engaged in the system, in the thinking process, help you to understand more. Okay, so I don't want to talk too much. I'm just going to do the demo and help you to understand physics concept this way. Okay, here goes. Here is a soccer ball. I hold it in my right hand. If I let go of soccer ball, it comes down because of gravity. Very good. This is a tennis ball. If I let go, tennis ball comes down because of gravity. Very good. Let's do a first test. I'm going to hold a soccer ball with my right hand, tennis ball with my left hand. I'm going to drop them at the same time. Questions? Which one comes down first? National Institute of Education taught all the professor. If you ask a question in the class, you must wait for 5 seconds. How many of you think that soccer ball will come down first? Raise your hand. How many of you think that tennis ball will come down first? Raise your hand. How many of you think that together? Raise your hand. Can we do the experiment? Let's do the experiment. Ready? 1, 2, 3, go. You see soccer ball come down first. There was one that did this at Science Center, small little boy in the audience. Sir, what? You cheater. You can anyhow throw the ball. I don't know how to throw properly. Okay, I did it wrongly. Right? I dropped the soccer ball first. Okay, let's drop it already. Okay, ready? 1, 2, 3. 1, 2, 3. Did you see that with your resolution of your vision, you can kind of say, oh, looks like the same. So this is where you can bring up discussions about the acceleration due to gravity, and you can derive a few things and say that, oh yeah, the acceleration due to gravity act on the object the same way. It's the same for different masses. Okay, yeah. Then, but different mass need more force. Yeah, because different mass means different weight. So those are the more force. So end up the mass term cancel out. So I hope you develop this kind of concept. Yeah. In fact, I can get a little boy to do a video. Let me skip this one. Okay, and show you in high-speed camera footage what happened. Look, this boy likes demo a lot. Yeah. Okay, you see, even under high-speed camera footage, right? The soccer ball and tennis ball seems to fall down at the same rate. Yeah. Sometimes I play this video, you're not paying attention to the soccer ball and tennis ball. Look at a small little boy, right? Okay, pay attention to the ball. Okay, yeah. Okay, this is my youngest son. Okay, yeah. Okay. By the end of the day, you can guess how many kids I have. Okay, yeah. Anyway, yeah. But it's about total picture. Some student will come to me, sir, this looks cool, but when I see a piece of leaves falling from the sky, it doesn't fall as fast, isn't it? Right? So now I have a book here, and in which I have a thin piece of paper. Ladies and gentlemen, I'm going to hold a book with my right hand and a piece of paper with my left hand. And I'm going to let go at the same time. This time, no cheating, really at the same time. Tell me, which one comes down first? The book. right? But just now tennis ball, soccer ball come down at the same time. Now you say the ball. Let's see, huh? Okay, ready? 1, 2, 3, go. Ah, indeed, the book come down first. So tell me, why is the paper not coming down fast enough? Ah, there is a very light, right? So, and then there is a lot of air resistance, right? Hey, wait. Air resistance not present for the soccer ball? Present, but the air resistance is so small compared with the weight of the soccer ball, not significant, right? So, okay. But the paper light, so the air resistance makes a difference, right? Okay, good. Now, let's test you further. Book, paper in front of the book, horizontal, and I'm going to drop. What happened? Book 4, paper float, or book 4, paper fall together with the book. Together. Remember the 5-second rule? 2, 3, 4, 5. Okay. How many of you say together? Raise your hand. How many of you say book 4, paper float? Raise your hand. You see? So there's no general agreement. Huh? I'll let nature tell you the answer. Ready? 1, 2, 3. Okay. You can reproduce the experiment. Do again. Do again. Do again. Okay. Think about the physics. If I do this, and therefore, which particular item will take the brunt of the air resistance? The book, do you agree? So from the point of view of the paper, do you appreciate that it does not experience any air resistance because it's taken care of by the book already? You see that? Okay. Now, let me hold the book with my right hand and the piece of paper with my left hand. Watch my left hand. 1, 2, 3. Questions. Have I changed the mass of this piece of paper? What did I change? Surface area. That means I reduce the air resistance. Agree? Let's watch. 1, 2, 3. Got it? The size physics is quite fun. Yeah. Okay. Yeah. Okay. Where did I go? Oh, what happened? Somewhere. Okay. Video. Okay. Can you see the video now? Yeah. So what my point is that physics is always regarded as something very abstract. I know, okay, I appreciate that you all think that, wow, sometimes when I learn physics, cannot understand what's going on. All this equation formula doesn't mean anything to me. Yeah. The student will face multiple challenges in developing concrete understanding and seeing the direct relevance of the ideas presented. So my goal is to illustrate to you the mind-on approach to learning of physics through all this fascinating and thought-provoking demonstration. Because, of course, you are excited, wow, interesting demo, but I really want you to understand the concept behind. Okay, yeah. We aim to achieve this by designing the learning experience. To start with, perhaps the most basic, you see, I just dropped the soccer ball, tennis ball. And then I move on to the next intermediate level, and then to the higher level. At some point, we even challenge you by giving you some kind of counterintuitive example. Okay, that is the idea. Yeah. Okay, this is done. Okay. Okay, so wait for some technical detail. Yeah. Okay, keep going. Okay, good. Yeah. Ignore the screen. Look at me. So you don't need any sophisticated instrument. Ladies and gentlemen, this is a bottle of water. Can those of you in front, can you see that there's a packet of chili there? Watch. 1, 2, 3. 1, 2, 3. There was one year I gave this demo at Science Center. A small little boy raised his hand. Sir, yes, can I come to the front and examine your finger? The little kid is very smart. He thought that I have attached a strong magnet to my finger. So I tell the little boy, finger is to bluff you one, no finger. 1, 2, 3. What did I do? I squeezed the bottle, isn't it? Right? So this is a very classical demo known as Partition Diver. Okay. So the purpose of this is to illustrate the laws of Archimedes Principle. It's about the laws of buoyancy. Any object partially or completely submerged in a fluid is buoyant up by a force equal to the weight of the fluid displaced by the body. The weight of the object acts downward, the buoyancy force acts upward. Okay. So that means if the fluid force balance, then object will float. Okay, Partition Diver is named after René Descartes for the creation of this thing. Yeah. So this is how I get you to start thinking. Yeah. Okay. Now I want to explain this in a simple concept. Let me use my hand to represent a packet of 3D. Anything on Earth, if you let go, it will go down because of gravity. Yeah. But when you go to the swimming pool, you jump into the water, you feel lighter, right? Because of buoyancy. Yeah. This chili packet is rather big. It goes in the water, it pushes the water away. This is called displacement. The water that can push away, not happy, push back, providing a floating force. Now, the floating force is happen to be able to balance the weight of the chili packet. So the chili packet floating. What did we do? We squeeze, right? The squeezing caused a pressure onto the chili packet. 1, 2, 3, squeeze. Do you see that the chili packet becomes smaller? Which means that the amount of water that it displaces becomes lesser. Which means that the floating force created will become lesser. This thing. So the moment you stop squeezing, boom, bigger. And then push more water, create more floating force. Simple explanation. Those of you with the physics one, I will start talking about different language. When I take the chili packet, put inside water, and I squeeze, the chili packet becomes smaller, right? Becomes smaller, right? Becomes smaller. So do I change the mass? No. Do I change the volume? The volume becomes bigger or smaller? Smaller. So the density is equal to mass over volume. Mass never change. Volume becomes smaller. So what happened to the density? Increase. Now the density happened to be more than 1.0 gram per cm cube. Somebody tell me, what is the meaning of 1.0 gram per cm cube? What is 1.0 gram per cm cube? Density of water. If you are denser than water, you sink. If you are less than water, you float. Yeah. Now, okay, let me ask you a very deep question. Okay, now move. Okay. Okay. What do you find inside a packet of chili? Chili lah, walao. Professor asked this kind of questions. Yeah. Think carefully. Only chili? Yeah. So when you squeeze the bottle and you compress the chili packet, are you squeezing the chili paste or are you squeezing the air inside? Okay. So when you squeeze, you are compressing air, compressing chili, compressing air. Okay. So how do you illustrate this point? You use this to illustrate this point. Now, this is too small for those of you far to see. I'll show a picture. Can you see? This is a plastic dropper. The top is, of course, air. Bottom is just red color water, okay? The line here differentiates between air and water. We use a pair of hot metal bar. We seal the top. Air cannot get out. And now one of such object is inside this here. Can you see that? So now let's test your concept. If I squeeze the bottle, it compresses the Partition Diver. The air inside becomes compressed. So what do you expect to see to the level of water inside this Partition Diver? Will it go up or come down? Up, okay, good. So now I stand here. Hopefully more can see. Can you see that the line in the middle differentiate between the two? 1, 2, 3, go. Not hard enough. 1, 2, 3, go. Can you see that it went beyond the black line? Right, and now if I let go, 1, 2, 3, go. It goes back down. So this tells us that yes, indeed, the air inside become compressed. Okay. Now I test you further. No in range. Okay. Okay, so explain it. Now I have another Partition Diver. This time I have 2 Partition Diver inside. 1 and 3. 1 and 2, sorry. What's the difference between 1 and 2? Different amount of air, different amount of water, right? So now, ladies and gentlemen, in front of you here, I have 1 and 2. I'm going to squeeze the bottle. I give you 5 seconds to decide. When I do so, which one will go down first? How many of you think A, plastic dropper number 1, this one? How many of you think B, plastic dropper number 2, this one? How many of you think C together? Okay, now I give you one more hint. Is it easier to compress water or is it easier to compress air? So these two, which one is easier to change the volume? Okay, good. So now you decide, huh? Good. This is number 1. This is number 2. Okay, see for yourself. 1, 2, 3. Number 1 goes down first because it changed the volume easily. More air inside. Number 2. Okay, got it. And let go. Then come back up. So I hope this way of teaching allow you to gain the concept better. But always challenge your student. Ladies and gentlemen, I have another bottle of water with a packet of chili inside. But the difference is this packet of chili is at the bottom of the bottle. Usually they stay on top. Watch what happened. Ready? 1, 2, 3. Wait a second. I squeeze, it goes up. This one, I squeeze, it comes down. And if I don't squeeze, it comes down. What the? Okay. So I need suggestions. What do you think is the main difference between this bottle and this bottle? Say again. Volume of air is different. What else do you notice being different? I heard that the shape is also not the same. Okay, now let me do it more obviously. What is the cross-sectional shape that you see? Circular. What is the cross-sectional shape that you see? Everybody agree this is like an oval or elliptical shape? Because this bottle has an elliptical shape, I'm going to use my hand to represent the elliptical shape. If you squeeze the ellipse from the side, what happens? Squeeze the ellipse from the side, it becomes rounder. Which means that if you squeeze this thing from the side, it becomes rounder. That means the pressure inside becomes lower. The chili packet now says, oh, I am experiencing less pressure, so I can expand a bit. When I expand a bit, I displace more water, I get more floating force. There it flows up. Is that clear? Yeah. So now I'm going to squeeze this bottle from the front and the back. You think the chili packet will go up? That means the elliptical shape, squeeze from the front and the back, it becomes like that. You think the chili packet will go up? Let's verify. You see that it doesn't go up if you squeeze this way. But if I squeeze on the side, okay, so I have a lot of interest in water. Every time I go with my wife to the shopping center, I always stare at bottles. Okay, yeah, and then I must declare I do not have any financial relationship with Listerine or Oral-B. Okay, yeah. Good. Okay, so we have done that. Yeah. So I hope you begin to appreciate. Okay, the way I learn physics, perhaps I can adopt a different strategy. Okay, yeah. Look at the pattern. Look at the phenomenon. Okay, reproduce one is very important. Okay, yeah. Come up with some logical explanation to explain what's going on first. Okay. You have to develop model. Don't worry, it may not be precise, the most accurate one, but you have to build on that. But yeah. Experience and enjoy the process of figuring things out. The eureka moment is priceless. When you understand, wow, I feel so enlightened. Yeah, man. Ponder the meaning of a concept and develop scientific insight. Okay, yeah. Go deeper. I always encourage students, go deeper. See whether you can discover more things. Okay, yeah. Okay. You can become very good in physics by adopting this approach to understand phenomena you encounter and trying different physics-related problems. Okay, and then you can slowly linking up here. Yeah. Now, I do not want you to get the wrong impression. You don't need mathematics. So physics is a module, it's a discipline whereby we have to use mathematics. Okay, this is a very important message for you. It is a critical part of physics. Okay, in fact, all sciences, not just physics. I would like to advocate for life science, for chemistry, for material science, for data science. You need mathematics. Okay, yeah. Develop mathematical model to provide even greater insight. Sometimes you can extract predicting future undiscovered phenomenon based on your mathematical model. Very powerful. Okay, yeah. Oh, okay, yeah. Okay, it can provide qualitative and quantitative insight. Does your math model predict outcome that has not been tested experimentally? And if so, you can test it and see if you can make new discovery. This is how advance of knowledge is made. Okay, in physics. Yeah. Okay. Of course, you can become very good in physics in doing so. Yeah. Okay. Now, we can also use technology to gain deeper insight into the scientific phenomenon. Okay, so for this one, I want to show you this demo. Okay. Ladies and gentlemen, what do I have here? I have here what we call a rigid body. Basically, two pieces of wood joined together at one end. Okay. When I do the demo, I'm going to raise this up and I let go. Is that clear? So now I'm going to support this thing using here and here. Is that clear? When I do the demo, I just pull. Is that okay? Good, yeah. So now, what is going to happen is that everybody, can you see there is a supporting structure here? There's a red cup. I'm going to hold a ball bearing and put it on top of this supporting structure. And I'm going to pull the rod. Don't blink, huh? This ball will fall into the cup. I cannot slow this down, okay? So prepare your eyes to stop blinking for 1 second. Ready? You ready? Okay. Ready, huh? 1, 2, 3. Yeah. Oh, okay. Too fast. Then do again. But unfortunately, I can't slow it down because nature dictates this. Okay, ready? 1. Ready? 1, 2, 3. So this is where technology becomes useful. Sir, too fast. Cannot see anything. Don't worry. Let's get some video done. We take video of this particular process, normal speed video. Too fast. But high-speed camera footage, oh, come. You see that? Let me do one more time. Ta-da! Isn't this cool? Yeah. So here comes the physics behind. This is the beauty of what we call rigid body. The whole thing, when it moves, it cannot bend. It's rigid. And it's pivoted at this point. Now, do you agree with me? Let me point to this point. In a certain fraction in time, it traveled maybe 2 centimeters. Let me point to this point. In the same fraction in time, this thing traveled 4 centimeters. Let's point to this point. The same fraction in time, this thing traveled 6 centimeters. Let's point to this point. The same fraction in time, this one traveled 8 centimeters. You get the idea? The further away you are, the faster is your speed, because the speed is related to how far you are away from the pivot point. Then it means your acceleration also, the further away you are, the faster is your acceleration. So that's condition number 1. Condition number 2. When it is disengaged, there's only one force that acts on this ball. What is that force? Gravity. What is the direction of gravity? Down. You realize? So the cup is exactly in the downward path of the ball. Okay. So condition number 1 is the cup below the ball. Condition number 2, the cup must fall faster than the ball. This is where this rigid body comes in. Because it's so far away from the pivot point, you work out the mathematics, 35 degrees is a magic angle. The cup will be faster than G. So then you do that. Okay. So I play the video one more time. After I play the video a few times, some students say, sir, the ball give me an illusion that it falls along the curved line. Like curved line like that, not straight down. You get the impression? Like, yeah. So how to elaborate this? No problem. You put a vertical rod behind like this, You do the same experiment. Oh, okay. My class must be like that one. I want the children, wow, okay, yeah, okay, yeah. Then I'm a happy guy. Okay, yeah. So yeah, indeed, all the concept checks out. Okay, yeah. Good. So to illustrate, the mathematical model is really, really cool. This is a rod. It has a mass m, so the weight is mg at a certain angle theta. And this thing fall down because it's pivoted along this point. So what you can do is that I will teach you the idea of rigid body. You can have a torque, which is a rotating force. The weight times the moment arm here, which is equal to half L cosine theta. Okay. Then torque is equal to moment inertia multiplied by your angular acceleration. Don't worry if you have not learned this, you come to me, I'll teach you. Okay, yeah. Okay. Then the moment inertia for this system is about 1/3 mL squared. L is the length of this rod. Okay. So okay, substitute inside. The angular acceleration is linked to the tangential acceleration, which is this A here by A over L. Okay, so a bit of algebra. Okay, that is my relationship between A and G. Fine. This point is going down this way. Okay, so I want it to go down vertically, which is A cosine theta, and I want the cup to catch the ball, so that A cosine theta better be faster than G. Okay, effective downward acceleration is A cosine theta. It must be faster than G to catch it. So you have an A here, you have an A cosine theta greater than G, substitute inside. That is a condition. G cancel out, angle 35 degrees. Wow, you see the idea? So maths is very important, okay? Good. So teaching physics, learning physics, I want you to appreciate this. You develop knowledge in a systematic self-discovery manner where you are constantly required to make sense of the phenomenon and thus forming a theoretical framework and model. You will find that I try not to teach you the formula equations directly. I want you to be able to formulate and generate that equations and formula by seeing things that happen in your eyes. Okay, so your own model is good because I didn't teach you. You come up with the model, so you own the model. Yet internalize the concept and you use it to tackle other problems. So this can provide good account of the observed phenomenon. When you do so, you develop this deductive and logical inference. Okay, so these are very important because we hope that this kind of skill set follow you for the rest of your life. Okay, yeah. Next, do you have this experience? Okay, this is when I teach electron magnetism. You are using your handphone. You're talking to your friend. Walk into the lift door shut. What happened to your handphone? No signal. Okay, yeah, okay, good. Yeah, so I try to receive signal from students. Okay, that means no signal anymore. It's not because your handphone no good, because a leaf is typically what we call a metallic cage. Okay, in E and M, electromagnetism, metallic cage is what we call a Faraday cage. It can shield the external signal. Here is a Faraday cage. 2 layer, 1 layer doesn't matter. I just happen to find this in the lab. Okay, ladies and gentlemen, here's a radio. You see, the radio was working fine, right? The moment it goes into Faraday cage, oh, no more signal if I take it out. Oh, a bit off. Okay, put it back in. 1. Okay, maybe I change a bit. Yeah, doesn't matter. Put it back at 1, 2. You get the idea? Okay, good. Yeah. So when I teach this, I will use it to illustrate the ideas of electromagnetic shielding and talk about Faraday's concept, Michael Faraday. Yeah. Then you ask, what is it good for? Well, next time you may be working for Ministry of Defense. Fighting a war, communication is very important. You do not want your enemy to send EM pulse to you to disrupt your communication. So you put your device into a metallic cage, protect your device from being interrupted. Is that clear? Yeah. Maybe I take it out, not loud enough. Yeah. Okay. I got to tell you, I'm not just a professor of physics in NUS. If I'm not doing my physics experiment, you know what I do? I go to community center and I learn Chinese Kung Fu. And after I learned Chinese Kung Fu, I developed some Qi Gong. You know what is Qi Gong? That means I can draw special energy from the universe. Okay. So, ladies and gentlemen, I'm going to draw special energy from the universe. I can put my finger up to the sky. Oh. Once I gather enough energy, I can direct the energy down. 1, 2, 3. Over here better. This radio doesn't want to cooperate with. Okay, let me turn on to a better channel. Okay. Hold on. Demonstration number 2. I gather enough energy. Oh, I said that already. Okay, energy gather. 1, 2, 3. So, do you believe that I have Qigong? Those yes are okay. I need to discuss with you later. Those say no one. Okay, good. I can discuss with you more. Okay, yeah. So I have no Qigong, but I don't tell you the answer. I'll let you figure out the answer. This is a piece of chopstick made of wood, conductor or insulator. I'm going to stick the wood in. You think the radio will work? 1, 2, 3. Nothing. Because insulator cannot conduct anything. This is a piece of metal. I'm going to stick the metal in. You think the radio will work? 1, 2, 3. Okay. And what do I stick in? 1, 2, 3. What is your conclusion about human body? We are conductor. Okay. So the radio signal, radio station signal is trying to make use of my body as a conduit for electric field to direct the electric signal to the radio and make it work. Is that clear? Yeah. So later I can invite everybody to come down here and you do your Qigong. Oh, and then put it here. Those of you who, put it here, no sound. Hospital checkup. What do you eat for lunch? Okay, yeah. Let me challenge you some more. This is a piece of wood. Very strange wood. How come this piece of wood can conduct electricity? Huh? Is this a piece of wood? It's a pencil. Oh, what is in the middle of pencil? Graphite, not lead, huh? Graphite. Graphite is a conductor. Okay, so now you use a graphite to conduct electricity. Is that clear? Okay, so, yeah. Don't worry, later we'll pick up. Okay. At the end of the day, the whole LT will be met. Good. So I hope now I have given you more flavor about physics, okay? Oh, this one is quite fun, must do. Candles in a bottle, okay? So, ladies and gentlemen, I want to illustrate this demo by showing you technology really helps, okay? Those of you near in front, can you see that I have 2 candles? Longer one is a blue one, shorter one is a red one, okay? So I'm going to put it here. During the demo, what I'm going to do is that I'm going to take a glass. I'm going to reverse it. Of course, I'm going to light the fire in the candles, and I'm going to lower the glass and then cover both candles with the fires let on. You get what I'm trying to do? Think. Tell me, which of the fire will be extinguished first? Okay, I think there's an MCQ. Yeah, okay. I'm going to light up both candles, long candle, short candle, invert the glass, cover. A, B, C, choose one. 1, 2, 3, 4, 5. Those of you who think that the fire in the blue taller candle will be extinguished first, raise your hand. Okay. Those of you who think that the fire in the red shorter candle will be extinguished first, raise your hand. And then those of you who think that both fire will be extinguished at the same time, raise your hand. You can see for yourself, right? I have 1/3, 1/3, 1/3, roughly. This is exactly why physics class is interesting, because different people think of a different logical reasoning, come up with different reason to arrive at the answer. Okay. And the good thing about experiment is that I don't have to say, I'm a professor, I say it, this is correct. No, I let the experiment tell you. Okay, good. Here goes. Candles, matchstick. Maybe dim down the light a bit. Thank you. Yeah. And sometimes I do stupid thing. Okay, yeah? You be a judge, okay? Make it pass, okay? Upside down. Ready? Oh. Gone. Still here. Gone. You see that? So what's the answer? A, go off first. Cool, right? Right. When you burn candles, what kind of air will be generated? CO2, right? Agree? So CO2, hot air rises, right? Okay, CO2 is denser than air, but hot CO2 rises still. Huh? Hot air rises, CO2 come here. Hot air rises, CO2 come here. But more hot air rises, CO2 come here, CO2 come here, CO2 accumulate, CO2 accumulate. Ah, do you see that? The upper column of the glass bottle now is all filled up with CO2. Can the fire burn? Cannot. But the bottom one, lower one, is not subjected to CO2 yet, right? So it still continues to light up. Then, of course, more and more CO2 until the whole thing is CO2. Then, I think, yeah. But do you believe me? I have to show you, right? So we go to high tech. Nowadays, because of COVID, we take a lot of temperature picture, right? So we get an infrared camera to picture what is the distribution of the hot CO2 air. Let me play this video. This one is just normal video. This one is IR camera for COVID. Watch. So long candle, short candle, fires already light up. Ah, see, we invert a glass jar and we cover the whole thing. You can already see the thermal hand, right? The hand. Okay, good. So now air, hot air is generated. A lot of CO2. And then the CO2, the hot air will rise, the higher temperature air will rise. Okay. Can you see that the upper portion of this construct is already green color? Those are the hot air, right? And you see that, yeah, oh, even turning red, that means even hotter air. Can you see that the upper candle, that means the longer candle, the fire is already submerged in all this air already? Yeah. Then, actually, very soon, you see. Can you see the fire is gone? Because it's submerged in all this CO2, I can't burn, I got nothing to burn. The one at the bottom, you see, it's not really subjected to CO2 yet, okay? So it can continue to burn longer because it's not influencing. Okay, okay, yeah. Then after some time, even the lower one also go. So I hope this way of visualizations and thinking about process helps. Okay, yeah. Good, let me move on, yeah. Okay, I have to watch time. Okay, next, let me just go a bit extra. Okay, the beauty of fluorescent solution. What is fluorescent? This one also, okay, light up first and then light down, okay. Fluorescent is a fun thing. It's the emission of light by substance that have absorbed light or other EM radiation. Is a form of luminescence. In most cases, the emitted light has a longer wavelength, okay. So let me teach you a concept. You don't buy expensive stuff, buy cheap stuff. Ladies and gentlemen, what is this? Sprite, okay. Ladies and gentlemen, what is this? Okay. I can't pronounce this kind of short, tony water. Okay, so maybe I get. Can you tell? See, straps. Okay, what is the words here? Contains quinine. Quinine is a fluorescence molecule. Sprite, on the other hand, just sugar. Okay. So now, ladies and gentlemen, I'm going to take another 2 glass jar. Okay. And then I'm going to take Sprite and pour in. It's really Sprite. It's nothing funny. Very nice. Okay. So Sprite go inside. Good. And now tonic water. Again, it's just tonic water I buy from 7-Eleven. Okay. Sprite better. Okay. Okay, good. So, ladies and gentlemen, which one is Sprite? Which one is tonic water? This one? Right, okay. I'm going to do the thing. Okay, your eyes must follow. Okay, ready? 1, 2, 3. Okay, which one is Sprite? Which one is tonic water? This one? Wow, your eyes very fast. You're all very young. Okay, I'm going to be faster now. Ready? 1, 2, 3. Okay, which one is Sprite? Which one is tonic water? Oh, there's no change. Okay, but let me go there behind. Now, which one is Sprite? Which one is tonic water? This one, yeah, okay. Let's use science. Ladies and gentlemen, in front of me, I have an ultraviolet laser pointer. You see now? You see also laser pointer? Okay. So I'm going to shine the ultraviolet laser light into a bottle of unknown solution. Let's see what happens. 1, 2, 3, go. Can you see a bit of blue color? This is just scattering from the blue ultraviolet light. Okay. So this is indeed Sprite, just sugar solution. Okay. Now, that means this one must be tonic water. Consists of quinine, which is a fluorescence molecule, right? Fluorescence molecule give you fluorescence. 1, 2, 3, go. Whoa, I become Jedi Master. Okay, fluorescence. Quinine molecules is a fluorescence molecule. You excite ultraviolet light, and now you can tell which one is Sprite, which one is tonic water. Okay, now I test you further. This is water. I pour water in. Decide for me. Do you think water will give you fluorescence? Can we test it? 1, 2, 3. See, water is not too fluorescent, right? Ladies and gentlemen, what is this? Highlighter, doing, highlighter, doing. Highlighter ink go inside, okay? And now, water with highlighter ink. 1, 2, 3. Whoa, I become Yoda. You know who's Yoda? What is the color of the lightsaber of Yoda? Green. Oh, ding, 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 ding. Okay, so you can do doing, doing, doing. Oh, you don't buy expensive stuff. You can go and buy Sprite. You can buy tonic water. Okay, yeah. If you cannot finish tonic water, you pass it with Sprite. I don't want. Okay, yeah. Isn't this fun? Okay, yeah, good. Next. Oh, I was going to ask a question, but never mind. Yeah. Oh, next one is fun. The sound of science, the science of sound. Okay, so object, because of the size and shape. Okay. Oh, 1 minute. Okay, sorry. Okay, almost there already. Almost done. Okay, yeah. Yeah, I made a lot of noise in my class. You can't fall asleep in my class. Okay, yeah. Object, because of the size and shape, because of the construct, because of the thickness, has its own natural way of vibration. This is called natural frequency. This is it. If I use a stick to excite this object, the stick is very rough. It may excite the object with all kinds of frequency. It may have perhaps one of the frequency matches the natural frequency of this object. So how it will vibrate violently. This is called resonance. Okay. So it takes a few seconds for resonance. Ready? Listen. Can you hear the resonance? Yeah. You don't need expensive toys. Seriously. You can buy simple thing and you can generate resonance. This is one of my favorite resonance machine. Ready? Listen. 1, 2, 3. Cool, right? Yeah, okay. This is a resonance pipe. It's corrugated. So when I sing, the air will be forced to flow in. The wall is dong, 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 dong. So the air will strike onto the wall, dong, 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 but regularly at the regular interval. So you create nice music. I'm going to cover this end of the pipe with my hand and I sing. Air cannot flow in. Do you think there will be music? Let's try. Get it? And now if I unblock it, I sing. You think air music will come back? Let's try. I gotta tell this. There was 1 year I finished a science demonstration at Science Center. I go home. Mrs. Tan called me. Mrs. Tan's son was in the audience during the science demo talk at the Science Center. Okay, so Mrs. Tan called, she was rather angry. Prof Sow, hey, hi, Mrs. Tan, how can I help you? Prof Sow, I'm very angry. Mrs. Tan, why are you so angry? Prof Sow, can you tell me why my son go to the kitchen and cut up the pipe to the washing machine? Your son is inspired to do experiment. It's okay, very good. Yeah, okay, yeah, let's do that. Okay, can this thing generate nice sound? Let's try. Nothing. And now, okay, this is quite cool, right? Yeah. Now, okay, leave the lights off. Okay, okay. Okay, good. Next, quite fun. What is this? What does it sound like to you? Drum. Okay, okay. How does a drum produce sound? Obviously, you strike and then the membrane vibrate, and they give you a sound, isn't it? Right. Now, if you look at it, can you see the vibrational pattern of the drum surface? Also easy, yeah. Can be complicated. Can be this only, or can be two parts. Can be this one, or 4 parts. Do you agree that the surface pattern can be complicated? Okay, so we now invent creative. I have 2 drums here. Those of you nearby, can you see that these are just PVC pipe? And I take balloon membrane, I break the balloon membrane, I cover both ends. That means one end each. Okay, this end of the PVC pipe, this end with the balloon membrane, can you see? Those of you nearby, can you see that there's a mirror in the middle? The purpose is to demonstrate to you the vibrational pattern of this drum. Is it okay? Good, yeah. So I have a laser pointer. I'm going to shine the laser light to the mirror. When the laser light hit the mirror, what will happen? Reflection. Agree? Okay. The purpose of this mirror is to illustrate to you the vibrational pattern of this drum. Okay. So now you don't have to look at me. You can look at the black screen. Okay. I need to mask off. Laser light. Laser light shine onto the mirror. Can you see the reflection? Okay. See, look, my laser light is pointing this way, so I'm going to shine it onto the mirror, and I get the reflection. Everybody get it? And now, how do I illustrate the vibrational pattern of this drum? Here goes. Do, re, mi, fa, so. This afternoon, a lot of people come and listen to this guy talking about Masterclass for physics. You see, I'm talking all kinds of frequency coming out. The pattern so complicated. The pattern is saying so, fa, mi, re, do. Oh, re is good. Re, re, do. What is the physics behind? When you sing, what comes out from your throat? Sound. How is sound propagated? Through air, right? So the sound will be transmitted to this membrane. So the membrane, in order to sustain the same frequency, it has to form a certain surface pattern, isn't it? And the mirror, which is stuck on the surface, will follow that particular pattern. And the laser light will follow that particular pattern as well. Okay, so you can do this. Do, re, mi, fa, so, fa, mi, re, do. And next time there is no more hand foot, never mind. Every one of you buy one of this or make one of this for yourself. And you just remember, do some pattern recognition. Hungry, 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 hungry. Whenever you see this pattern, that means it's time to meet up at the canteen. Okay, good. Now, I would like to move on to my last item. I know that I'm overrun, but this last item is very important. Okay, so let me do the last item. Okay. Maybe I have a bit of light on. Okay, maybe I do here. Ladies and gentlemen, this is basically just a light source, okay? And I support it here. Okay, this is my last one. Okay, after that, I'm done. Yeah. Okay, and then I plug here. You see that it's very bright. Okay, so what is this? This is a device to blind my student. Wow. Okay, good. Not blind enough. Blind some more. Wow. Okay. So let me switch it off first so that you don't get blinded. Yeah. This is about the physics of polarizer light. Okay, so this is a polarizer. When light passes through the polarizer, the electric field will only go in one direction. So if I have two pieces of polarizer, if the two polarizer has the same direction, light will still pass through. Can you see my face? Can you see my face? Can you see my face? 1, 2, 3. Can you see my face? 1, 2, 3. Whoop. Whoop. Okay. Whoop. Whoop. Okay. Yeah. So when they are crossed, light cannot pass through. Yeah. So here is another piece of polarizer. Right. Okay. Now, when this light source passes through the polarizer, the light passes through polarizer, can you agree that the light is polarized? Polarized light is very useful because we can use it to study many, many different things. Okay, so what is it, many different things? This is a piece of plastic. Do you agree with me there is a stress and strain in this particular piece of plastic? But can you tell where it is? No, right? So you can put this thing through a polarizer like this. Okay, and you let polarized light pass through. Now we can switch off the light. Okay. And then the polarized light, if you recombine them later, you'll be able to see the stress and strain in the system. Ready? 1, 2, 3. Can see? Oh, can see? Okay, good. So, the physics of this, do you have 3 hours? Because it's very complicated. I need to explain for 3 hours. It's about how light travels in the material. When the material is stressed, it has different refractive index. Different refractive index means speed of light is different. Speed of light difference, that means the way they mesh combined together later will be different, color dependent. Okay, so that is the main gist of it. And the cool thing is you can put this thing here. Can you see this is a perspex? You don't know that there's stress and strain? Can you see the stress and strain? 1, 2, 3. Now, if I turn 90 degrees, things will change. 1, 2, 3. Okay, so here and here. Okay, those of you here and here. Okay, can I have all the lights on? Yeah. There is some benefit to attend physics class. Physics boss tends to be a richer. Okay, so now I'm going to give every one of you a free gift. It is 2 pieces of polarizer or 1 piece of polarizer with some plastic knife and over there. When you receive this, open it up, look through the plastic knife with your polarizer, and you'll see beautiful color. Okay, good. Can we help to distribute? Yeah. Okay. Distribute. Okay. And that is the end of my class. So get the item first, open it up, look at this. You can see beautiful color. I think after that, you can go. Oh, no Q&A. I will stay back for Q&A. Yeah.
Okay, that brings us to the end of today's masterclass. Thank you all for joining. And just pass by Anna at the left side to collect your goodie bag from Prof.
Yeah.
And for those who have questions, do stay back.
Yeah,
but in interest of time, we'll let the rest go. Thank you once again for attending and have fun at NUS Open House.
I hope to see you in NUS in the future. Okay. So on your way out, you can pick up the item. You just need to look at it through your any light source. You'll be able to see the colorful thing. Yeah. Or you can pick it and come here and test. Those of you who have questions, you can post. I can still continue to answer. Yeah. How do I learn quantum physics? What course must I take? Don't worry, you have to take quantum mechanics as compulsory course anyway. Yeah, so you will have a lot of quantum physics learning. what marks do I need to learn quantum physics? We don't have any so-called incoming cutoff point for quantum physics. Yeah, so you are once you are CHS student, you are welcome to take quantum mechanics. Yeah.